Those, welcome back. Hope you had a chance to watch the flame test videos. It's sort of interesting, isn't it? Sort of surprising. Of course, if you've ever watched fireworks before, you've seen these colors, but have never realized what made those colors, and so now you know. So, what color was the sodium flame? Do you guys remember? Yeah, it was a yellow flame, wasn't it? Sodium compounds give off yellow flames. What about potassium? Yeah, we call that violet. Sort of looked like a very light purple, didn't it? Copper, a lot of kids say this is their favorite. Yeah, that was an emerald green flame. So the next time you guys see green fireworks, you know that there's some copper mixed in with that gunpowder. Strontium? Yeah, that was a reddish orange. And then my personal favorite, which was lithium, which was a pink flame. Some people call it fuchsia. I'm not sure how to spell fuchsia, so can I stick with maybe a pink colored flame? Well, according to Bohr, what caused those different flame colors? That's right, it was electrons moving from high to low energy levels. And when they fall from high to low energy levels, they give off energy in the form of visible light of different colors. So pretty interesting. Hopefully you guys enjoyed that demonstration. Okay, let's go on to the next page here, and let's officially draw or have a drawing of Bohr's model. So we have energy levels. Here's the nucleus, of course, right in the middle. And then there are energy levels surrounding that nucleus where the electrons spend their time. And they can go from one energy level to another energy level. If they're excited, they move up. And as they fall back down, they give off energy, sort of like moving up and down a staircase. You can see in this illustration here, if an electron's on the third energy level and it takes a trip down to the second energy level, it gives off energy, doesn't it? But what if it were to go in the other direction? Yeah, it would take energy, wouldn't it? Well, we can determine the energy that was required by examining the light that was given off, right? And understanding its frequency, because doesn't frequency help us understand the energy? If you recall our discussion on frequency, wavelength, and energy. Now, Bohr also learned a few other things about the electrons as they orbit the nucleus of the atom. He learned something that we now call the 2n squared rule. And the 2n squared rule helps us determine the number of electrons that are possible on each energy level. So each energy level can only hold a certain amount of electrons. And this 2n squared rule helps us figure that out. N, of course, is the energy level number. So if I'm on the first energy level, the 2n squared rule would tell us that we can hold a certain number of electrons there. N is 1. 1 squared is 1 times 2 means 2 electrons can be held on the first energy level. What about on the second energy level? Well, N is equal to 2 now, isn't it? 2 squared is 4 times 2 means 8 electrons on the second energy level. When N is equal to 3, so N would be 3. 3 squared is 9 times 2 gives us up to 18 electrons can be held on the third energy level. Let's do one more just for fun. The fourth energy level, N would be 4. 4 squared is 16 times 2 gives us 32 electrons can be held on the fourth energy level. And so on. It's called the 2n squared rule. Now, it's interesting to note that these energy levels can hold up to that number of electrons. However, they reach a stable state oftentimes with less electrons. For instance, on the third energy level, that energy level becomes stable. And we'll talk more about what stability means in an upcoming video with 8 electrons. And the same is true with the fourth energy level. It becomes stable with 8 electrons. In fact, that can be said about energy, any energy level after the first, that it becomes stable with 8 electrons in it. And you'll notice when we start talking about noble gases that they will always have in their highest energy level 8 electrons. There's something very stable about having 8 electrons, or we like to say 4 pairs of electrons in that farthest energy level. All right, so let's talk about quickly what valence electrons are. What are valence electrons? I just used that term a moment ago, and let's define it for you. Valence electrons are electrons in the highest energy level. They're the electrons in the highest energy level. And we can determine the number of valence electrons pretty simply. I'm going to give you the shortcut, and then we're going to explain why it works. To find the number of valence electrons in an atom, it's simply the last digit of the group number of the element. Now, that does not apply to groups 3 through 12. Those mostly have 2 valence electrons. So groups 3 through 12 mostly 2 valence. But the other groups, we can determine the number of valence electrons by looking at the last digit of the group number. Now, of course, that won't work for helium. Helium is in group 18, so you might think it would have 8 valence electrons, but you have to remember helium only has 1 energy level, so it has 2 valence electrons. So how do we figure this out? How does this work? Well, let's talk about a couple of different elements. Let's take, for instance, let's go with neon, okay? The atomic number for neon is 10. So the way we abbreviate atomic number is Z. So we'll say its atomic number Z equals 10. And if we take a look at the nucleus and just draw that right there, and then put in 1 energy level. If it has 10 electrons, can't I hold 2 in that first energy level? Okay, all right. It still has 8 more, and I can fit all of those 8 in the second energy level, can't I? 2 plus 8 gives me 10. That's the number of electrons neon has. We have 2 in the first, 8 in the second. So we would say that neon has 8 valence electrons. It happens to be in group, if you look at your periodic table, 18, 8 valence electrons. Here, let's pick another one. Let's do argon, okay? Its atomic number is 18. So we'll draw the nucleus here, and the first energy level, of course, can hold 2. The second can hold up to 8, so I have 10 so far of my 18. So in the third energy level, won't I have 8 more to get all 18 electrons in there? So we'd say that argon also has 8 valence electrons. And it happens to be in group number 18 again. Here, let's pick another one. Let's do sodium. All right, the atomic number for sodium is 11. So here's sodium's nucleus. In the first energy level, there can be 2 electrons. In the second energy level, we can have 8 more. That gives us a total of 10. So don't we have to have 1 in the third energy level? We do. So we'd say sodium has 1 valence electron. It's the electrons in the highest energy level. Sodium is in group number 1. Look, it worked again. The last digit of the group number can help you find the number of valence electrons for that element. Here, let's pick chlorine. Chlorine, atomic number 17. Here's its nucleus. So 17 electrons. Can't we fit 2 in the first energy level? 8 in the second energy level? And we can squeeze 7 more in that third energy level to give us a total of 17, right? So the valence level has 7 electrons in it. So we say that chlorine has 7 valence electrons. And it's in group number, guess what? 17. It works again. Let's do one more since we have a little bit of space available. Let's do silicon. Silicon's atomic number is 14. Here's its nucleus using our Bohr model. 2 in the first energy level, 8 in the second energy level, and the last 4 we can put in the third energy level. 2 plus 8 plus 4 give me 14, but the number of valence electrons would be those in the highest level, so we'd say silicon has 4 valence electrons, and it's in group number 14. So we can find the group number, or the number of valence electrons, by using the Bohr model and his 2n squared rule, and knowing that energy levels become stable with 8 valence electrons. Or we can look at the last digit of the group number. Now there's actually much more to this than what I've explained to you, and that helps, and that leads to something called the electron cloud model, which is actually our current model of the atom. And for this class, it's beyond the scope of this class. So when you're a junior, you can take honors chemistry, and we'll talk about this electron cloud model of the atom. Okay? All right. That's it for today, kiddos. We'll talk to you soon. Bye-bye.